Hello everyone. Now let me apologize in advance if this is a longer video because I know we're not spending class time on this. If you do take the time to go through these notes and work through the practice problems, make sure you share that with me because then you'll get extra credit for doing that. Because remember how we talked about 8.4, if you have the time, wonderful, go through it. If not, no worries. Okay, so here's the idea on this. And I know this flow chart might be hard to see. I'm on page 25. So we have talked about finding pH of strong acids and weak acids and strong bases and weak bases. And we've even calculated pH values and concentration values when we're at the equivalence point, when the moles of the acid equal the moles of the base. Now what 8.4 is not knowing if we're at that equivalence point yet. That we're going to, for each problem in 8.4, some moles of acid will be added to moles of base. And we have to decide what is going on. So let's say that we add moles of acid to moles of base, and we find out that there was excess of a weak acid or a weak base. Then we're going to use that Henderson-Hasselbalch equation that we worked with last class. Now, if there's no excess, if the moles of the acid equal the moles of the base, this is the hard one where we have to do an ICE table to be able to get to our final calculation. And then I honestly believe this one is the easiest. When the excess, either the acid or the base is strong, then we just do our pH on this one. So we're going to look at each of these pathways and work through a couple of those problems. I'm going to be flipping back and forth to that, and then also remember that I have the same table on the back of your packet. Okay, so 250 milliliters of 0.35 molar hydrochloric acid is mixed with 150 milliliters of 0.5 molar sodium hydroxide. Write the net ionic equation for this reaction and find the pH of the final solution. So reminder, when we have a strong acid like HCl, we don't have to include the Cl. We can just change it to H plus for the net ionic. So even H plus aqueous is mixed with sodium hydroxide. That's a strong base. And again, a reminder, when we have a strong base, then we don't have to include the sodium part of that, right? The metal part of that. We can change it right to an OH minus. So our H plus and our OH minus are going to turn into H2O liquid, okay? And we are going to use a BCCA table, not an ICE table, a BCCA table, to figure out if these items, did we have perfect amounts of them, or is one of them an excess and one's a limiting? And that's how we use a BCCA table to figure that out. Okay. Reminder about a BCCA table and how it's different than our ICE tables. We do include liquids and solids in BCCA tables, and we can only have moles inside of a BCCA table, and that's another important difference here. Something we've done quite a bit. Whenever you see a volume and a concentration, your mind should be thinking moles. Like I'm going to take this 0.2500 liters and times it by 0.35 molarity, and that's going to tell me the moles of the HCl. 0.25 times by 0.35. So we have 0.0875 moles of our hydrochloric acid. Okay. That is before the reaction. Before the reaction, there are this many moles of the acid. Doing the same thing for the base now. 0.1500 liters times by 0.50 molarity. So we have 0.075 moles of our base, of our sodium hydroxide. Reminder, with strong acids and strong bases, the moles of the acid equals the moles of H+, or the moles of the base equals the moles of the hydroxide, 0.075. Okay. Molarities, those go in ice tables. Moles is what goes in BCCA, and we started with 0 products. Our coefficients tell us what this change is going to be, same as the ice table. So this is going to be a minus x, and then a plus x. So we have 0.0875 minus x and 0.075 minus x and a 0 plus x. Okay. One of these reactants is going to run out first. Okay. One of them is our limiting, and we figure out which one by solving for x. We set both of them equal to 0, and then we solve for x. So for the acid, we have 0.0875 is equal to x, and for the base, we have 0.075 is equal to x. Well, reminder, the smaller x value is the true x value. Okay? So that means the small x value is the true x value, the bigger one is not. So the base was the limiting. That's the thing that we ran out of. So for the acid, this does not actually equal 0. So let's see what it is. 0.0875 minus 0.075. So we are left with 0.0125 moles of that acid. Now 0 plus x is just equal to x, and now we know what x is, so that's how many moles of water. Okay, great. So what we just found out is we took a strong acid and a strong base, and our excess was the strong acid, right? So our excess was the strong acid. We used a BCCA table to figure out which one the excess was. And so now we're going to use the concentration to determine the pH. Okay. This is how many moles of H plus we have. So like if I want to get this concentration of H plus, I'm going to take the moles, and then we divide that over the total volume. And the volume was 250 milliliters plus 150. So like 250 plus 150. So we get 400 milliliters, which is 0.400 liters. Okay, I'm running this number. So our concentration is 0.03125 molarity. Okay. And then to get our pH, we would do the negative log of that concentration of H plus. Now, before I do this, just a reminder, we had 4 sig figs, 2 sig figs, 4 and 2. So I'm dealing with 2 sig figs right now. Okay, so it's like here's my 2 sig figs, and then I'm going to do the negative log of this number. And just a reminder, when you have a log number, the first digit is not significant. So 1 point, and so then I need 2 significant figures after that. 1.51. That's my pH value. This makes sense because we were left over with a strong acid, so we'd expect the pH to be relatively low. Okay, next. What if we have a weak acid and a strong base? Like, what would this net ionic look like? So we have some kind of weak acid. Now, a reminder, when it's a weak acid or a weak base, we don't have it break apart. Okay? And then we have a strong base that does break apart, and we'd really only need to keep the hydroxide part of that when we're doing our net ionic, and that's aqueous. Okay? So what happens is the H plus breaks off of the A minus, and then it's going to be gained by the OH minus, by the hydroxide. And so what we're left with is water, liquid. And then the other item is this A, and it's an A minus, our conjugate base to that acid. So this is generally what we should see when we have a net ionic equation between a weak acid and a strong base. So on this next one, equal volume of 1 molar HNO2, a weak acid, because HNO3 is a strong acid, and 1 molar of potassium hydroxide are mixed, right? The net ionic. So here's my weak acid, and I don't break it apart for a net ionic because it's weak. And then my strong base, so I do break it apart and I only keep the hydroxide. And then we're going to get water, liquid. We're going to get water, liquid, and then NO2 minus, aqueous. Okay. Identify the aqueous species that have the highest concentration at equilibrium. And so we had equal volumes of those items. How about for now, let's do a little calculation. This will be interesting. Let's make the assumption that equal volumes, so we're going to say that we have 1 liter of each. Okay, we're going to assume 1 liter because that makes our math really easy. So what if we were calculating pH for this again? Oh, is this where we actually don't have any x's because they're the same? Yeah, okay. So we don't want to, let's hit pause on this one. We're not going to do the pH on this one because we'll have equal moles of this and this. And so then that leads us to that longer one. But to answer the question, what is the highest concentration at equilibrium of the aqueous items? Well, this is going to completely react and that's going to completely react. These things are not going to be present in the solution if we have equal amounts of them because all of them, or all but all of them, are going to turn into these items. And then liquid is not an ion, and so we have just extra water, and so this is the aqueous species that will have the highest concentration once we get to equilibrium. When it's an acid and a base reaction, we're not getting this back and forth, really. Like, the forward reaction is so much bigger than the reverse reaction, that when acids and bases are present, they react and they become water, and then what other ions or ionic compounds we make. Okay. We're skipping number 3 because it's really similar. We're moving on to number 4. So we have 55 milliliters of 2.5 molar sodium hydroxide, a strong base, is added to 55 milliliters of 2.0 molar hydrofluoric acid, which is a weak acid. So we're taking a weak acid. I didn't break it apart because it's weak, plus the strong base, so I only keep the hydroxide. And that's going to turn into water, liquid, and then our conjugate base, our F minus, aqueous. Okay, so we're going to figure out which one's excess and which one's limiting. You might already be able to tell, but we still need to do the calculations because we need to know how much of this there's going to be. So we're going to do our BCCA table. Alrighty, now, the hydrofluoric acid, there's 55 milliliters of 2 molar. So I'm not even gonna write this part down. If it was a free response, I would, but we're gonna get the moles of that. So I'm gonna do 0.055 times by 2, my volume in liters times by my molarity, and there's my moles, only moles in a BCCA table. So before the reaction, I have 0.11 moles of the acid. Okay, same thing for the base, 0.055 liters, but this time it's multiplied by 2.5, because that was our molarity for our base, 0.1375 moles, 0 and 0. So our change is going to be minus x plus x plus x. We get 0.11 minus x, 0.1375 minus x, 0 plus x, 0 plus x. Okay, That's the change. Now, one of these, we can probably already see it, of the reactants is going to equal 0. One's going to be the limiting, one's going to be the excess. So I'm going to calculate that x value. So that 0.11 is equal to x, and 0.1375 is equal to x. The smaller x value is the true x value, the bigger one is not, so this one does not equal 0. The acid is the limiting, the base was the excess. So now that we know what x is, though, we can plug it in. So 0.1375 minus x minus 0.11. So we're left with 0.0275 moles after the reaction. 0 plus x is just equal to x, and we know what x is, so this is how many moles of these other items we have. So we mixed an acid, a weak acid, with a strong base. And what the excess was the strong base, not the weak acid. So when the excess is strong, we're going to use the concentrations to figure out the pH. Now, if it's a base, we're going to find the concentration of hydroxide, and then once we have our pOH, we'll find the pH. If it was the acid, we get the concentration of H+, and then just do the negative log of that. But we have a base. We have hydroxide. So concentration of hydroxide is equal to the moles of hydroxide, 7.5 moles, divided by the total volume. So 0.055 plus 0.055. So we have that many liters. This is 0.25 molarity. And then if I do the negative log of this hydroxide concentration, that's going to equal pOH. Okay, now keeping track of this, this is two significant figures. And so the leading digit for a p-value is not significant. It happens to be a 0 on this one, so 0 point, and then 60. Okay, that's my pOH. And the final step to get my pH, because it's asking for pH, is to do 14 minus our pOH. So 14 minus our pOH, 13.40. And this is a high number. It makes sense, though, because we were left with a strong base there. That's what was excess when it was all done. Okay, good. We've already used this equation quite a bit, so and we spent time, we've even written notes on this page. So just a reminder, this is the concentration of our weak acid, this is the concentration of its conjugate base, and then pKa equals pH. Okay, so we're on example number 5. We have 20 milliliters of 1.5 molar potassium hydroxide, that's a strong base, and it's added to 50 milliliters of 3 molar acetic acid, that's a weak acid. They give us a pKa for that acid, and we're asked to find the pH. So we need to figure out which one's in excess. Do we have excess weak acid or excess strong base? So we're going to write out our equation here that we've been talking about, where if it's a strong base, we just take the hydroxide. If it's a weak acid, then we need to take the whole thing. That the H plus is going to leave and go to the hydroxide to make water, liquid, and we're left with the conjugate base of that acid. We're going to do our BCCA to figure out which item is limiting and which one is excess. So that's going to be my starting. Okay. I'll write this one down just so we can remind ourselves and see. So to figure out the moles of potassium hydroxide, because again, BCCA table, only moles. So I'm going to take the volume in liters and I'm going to times it by the concentration. Okay, so 0.02 times by the 1.5. That is how many moles I have of this base. So I'm starting with, before the reaction, 0.03 moles of the base. Now we're going to do this exact same thing for the acid. 0.0500 liters times by the molarity. And this is how many moles I have of the acid. 0 for my products here. We're getting a minus X value and a plus X value. So it's going to be 0.03 minus X, 0.15 minus X, 0 plus X, 0 plus X. One of these reactants is going to be equal to 0. One's the limiting, one's the excess, and we're going to calculate that. So we have 0.03 is equal to X for the base, and 0.15 is equal to X for the acid. And we go, oh, the smaller X value is the true X value, the bigger one is not true. So this one doesn't actually equal 0, this one does. So base was the limiting, the acid was the excess. So let's figure out how much this is. We're going to do 0.15 minus X, which is 0.03, and so we're left with 0.12 moles of our weak acid. Okay? 0 plus X is equal to X, and we know what X is, it's 0.03. So that's how many moles of water we made and of the conjugate base. So we are left with excess weak acid. See what it says. If the excess is weak, oh, then we're going to use that Henderson-Hasselbalch equation. All right, great. So we need a couple of things for that equation. Let's write the equation down first to remind ourselves. pH is equal to pKa plus the log of the concentration of the conjugate base over the concentration of the acid. So we know the pKa because it told us up above. The pKa is 4.8. Now we need to find out the concentration of the conjugate base. And the conjugate base is CH3COO minus. And then we need to find the concentration of the weak acid, CH3COOH. And once we have those things, we'll be able to calculate the pH. The good news is that we know the moles of both of those items. CH3, oh my goodness, can't write right now. CH3COO minus from our BCCA table. So we know after the reaction, this is how much of that conjugate base we had as far as moles go. So 0.03 moles. And we know the total volume. 20 milliliters plus 50 milliliters would be 70 milliliters, or 0.0700 liters. So our concentration is going to be 0.428, etc. Here's my concentration of my conjugate base. Now let's do the same thing for our weak acid, CH3COOH. And after the reaction, we had 0.12 moles of the acid, and it's the same total volume. So our concentration is 1.71, etc., molarity. So now the final step is getting that pH, is plugging those numbers into that equation. Like pH is going to equal pKa, which is 4.8, plus the log of the concentration of the conjugate base, which is 0.428, divided by the concentration of the acid. I'm going to use the long stored numbers, and then let's talk about sig figs. So 4.8 plus the log of this one divided by that one. Okay, now, without sig figs, 4.197. Going, two things I'm checking. First thing I'm checking, going back here, 2 sig figs. And then also the pKa, though, only has one digit after the decimal. So as far as this like log goes, because remember how whenever it's a log number, we'd want 2 digits after the decimal because it was 2 significant figures, but then we're adding it to something that only has 1 digit after the decimal. So I don't think they would choose a question like this to be the sig fig question, but the final answer would actually be 4.2. Okay. Now, logically, this number makes sense because it's below 7, because we had excess of a weak acid. And then, but it's weak, right? It's not strong. It's not going to be a pH that's closer to 1. It'll be a pH that's closer to 5. It's going to be higher than a strong one. So that would be a reasonable number as far as pH would go. Okay, nice. You're doing good. Okay, so this is the big one. This is we use a BCCA table and we find out that there is no excess. And so then we're going to have to use an ice table to follow it up to finally get our pH or pH. So let me walk you through it. We're going to go slow and I'll explain why the ice table's needed when we get there, because it's just easier to see it once we have it all written out. So like we've always been doing, anytime you see that an acid is being mixed with the base and it's not specifically telling you that it's at the equivalence point, then we should do a BCCA table to see what the limiting and what the excess is, if there even is a limiting or an excess. So we have a 30 milliliter sample of 0.5 molar of the acetic acid is mixed with 30 milliliters of 0.5 molar sodium hydroxide, the strong base. We've talked about what the equations look like when it's a weak acid and a strong base. Right away, you can probably already tell that there's not going to be a limiting because we have equal amount of moles of both of these things. Okay, that's wonderful. I need to get a number from my BCCA table though, so we're still going to write this out. We're going to take a number with us. All right, so here's the equation. BCCA. Getting those moles for both. It was 30 milliliters or 0.0300 liters times by 0.5 molarity. So as far as moles goes, we have 0.015 moles that we're starting with both of those. We're going to have a minus x and a plus x. 0.015 minus x, 0.015 minus x, 0 plus x, 0 plus x. And we're going to see that both of them is 0.015 is equal to x. They are both the smallest value, so we don't have a limiting or an excess. Like they're consumed at the exact same amount and rate. And so then 0 plus x, and that x value is right there. Okay, great. Now, something interesting though. So when both of these things are consumed, we made something. We made water. That's not really going to make an impact on the pH, but what is this conjugate base. We have put conjugate base into the solution. And so this conjugate base, we had to see what it's gonna do now that it's there. That if it's in the presence of water, a small portion of it's gonna revert back to that acid, and we need to know how much. That's where we get this equilibrium reaction. Like we're dealing with a weak acid or a weak base, and so then we get this back and forth that some bit of this is going to go back to that weak acid. Okay. We were told what the Ka was. So it says the Ka for the acid is right here. But notice what we have is its conjugate base. So we're going to find our Kb value. Now what's cool is on here, right here, Kw equals Ka times by Kb, and we know what our Kw value is. So we know Kw at 25 degrees Celsius, which is, even if it didn't say, we can assume, but this one it did tell us, actually said 25 degrees, is 1 times by 10 to the negative 14. And we know that our Ka is 1.8 times by 10 to the negative 5th, and we're going to solve for our Kb. So Ka times by Kb equals Kw. Solving for Kb, so Kb is equal to Kw divided by Ka. 1 times by 10 to the negative 14 divided by 1.8 times by 10 to the negative 5th. And we have a Kb value of 5.5, repeating, times by 10 to the negative 10. All right, great. We're going to use that number in a little bit. So this bit of base, oh, yeah, sorry, before I write that down. That little bit of base is going to react, okay? But before we do that, we are in an ice table, and those are moles. So a couple of things. First off, if we have liquids or solids, we don't include them in our ice tables. And we can only put concentrations or pressures inside of our ice tables. So let's actually calculate this concentration of this conjugate base. Okay, we're going to get this concentration. So we know the moles, 0.015 moles. And then it was 30 milliliters plus 30 milliliters, or 0.0600 liters. So we get a concentration of 0.25 molarity. So concentrations are what go inside of ice tables. We get 0.25. 0 for our products. Okay, we have our change and then our equilibrium. Initial change, equilibrium. So this change is going to be our minus x plus x plus x, 0.25 minus x, x and x. But we're dealing with a weak acid, and here's our Kb, here's our conjugate base value. Look at how small that is. So remember how we can make that assumption that the little bit that we're adding there is just like nothing compared to this original concentration. And so then our Kb expression would be this guy multiplied by this guy divided by this one. So x times by x, or x squared, divided by 0.25. Okay, let's rearrange and solve for x. So 0.25 multiplied by our Kb value, square root, equals x. So we're going to take 0.25 times by our Kb value. We're going to do the square root of that. So x is small. It's equal to 1.178, etc., times 10 to the negative 5th. Okay, molarity. Now, looking here, that is how much hydroxide there is. Okay, so this is equal to the concentration of hydroxide. So if we, final step, if we do the negative log of this concentration of hydroxide, that will tell me my pOH. Negative log of this number, 4.928, etc. To get pH, we do 14 minus our pOH. 14 minus this number. Okay. Now, sig figs. I'm going back all the way to the beginning, and I'm seeing 2 sig figs as our smallest one. Yeah, and so then whenever we have a p value here, the first item is not significant, so we have a 9.07 for our final pH. Okay, nice. Okay, so everyone, the second half of this is doing what we just did with bases instead of acids, but we don't need to walk through this process again. We are just looking at what if it's a strong acid with a weak base now, where before it was a weak acid with a strong base. But it's the exact same idea. It's just you might be getting to pOH first and then your pH. So it just would change what you're doing at the very end there. Okay? So I don't think we need to do this second half. Let's make sure we're okay with our net ionic, though, so that you can use it to do your BCCA tables. So where you're taking a weak base and a strong acid. So reminder, with our strong acids, we did just do an H+, aqueous. But our weak bases, our weak base here, whatever might be in there, that is, think of the phrasing here. It's in its entirety. We're not breaking it apart. It likely might not even contain hydroxide. It could, but it probably doesn't. And so this is our base, okay, aqueous. Now, weak bases accept protons from strong acids. And so that makes our net ionic pretty simple, that this is our conjugate acid, that it just accepts that H+ from them, where this is our base and that's the conjugate acid. So whenever I would be writing out equations to do BCCA tables and it's at a strong acid with a weak base, that would be my combination. That would be my approach there. Okay, nice. I'm going to, I'll have hard copies if you want one, but I'm in this email, I'm also going to send the link to the video as well as the practice problems, okay? And so make sure if you want the extra credit, walk through those practice problems as well. Do the best that you can with them. Feel free to come ask me, get help, come check the key that I'll have. And once we get these notes done and you do those practice problems, then check those off with me and I will give you 10 points of extra credit because that's a lot of work. So I definitely want to give you a good reward that's equal in magnitude. So thank you. If you have any questions or concerns, please do not hesitate to come talk to me. Right.